Okay, Assalamualaikum warahmatullahi wabarakatuh. So now we look at the topic 4 part A, the new topic. Okay, so analysis of flow in pipes. Okay, so learning outcomes. So at the end of this chapter, students should be able to understanding of laminar and turbulent flow in pipes and the analysis of fully developed flow. So calculate the major and minor losses with pipe flow in piping networks and understand the difference velocity and flow rate measurement techniques. Okay, introduction for this. So we look that these figures show example of flow in conduits and this chapter will be discussed further on closed conduit flow. So this is the example of conduits. Okay, this is open flow channel and the channel flow in the flow pipe. So this is the open channel flow open to the atmosphere. Okay, channel flow in the pipe here and also closed conduit flow. So this is the full of the closed conduit flow. So also limit to incompressible fluid with constant density. Okay, 4.1 is characterization of flow based on Reynolds number. Okay, so based on the Osborne Reynolds, a British engineer conducted a flow experiment. So the flow experiment here by injecting dye. So the injecting dye into a pipe flow to classify the types of flow. Okay, based on the injecting dye here, so the from the experiment can identify that the flow is laminar, turbulence and transitional. Okay, so Reynolds experiment is based on the apparatus here. Okay, so based on the dye here and the water here based on the pipe here. Okay, after open both valves, dye flows through the pipeline until the middle of tank's outlet pipe nozzle. Okay, what happened to the flow? Okay, so the flow here. Okay, outlet pipe opens into the middle of the tank's outlet pipe. So they have this is the result. Okay, when the open valve here, the dye container here. So with the smooth line here is called laminar flow with the smooth line. Okay, based on the fluctuation line here is transitional flow and the turbulent is more fluctuation. Okay, so this is the result for the laminar flow, turbulent flow and transitional flow. Okay, so based on the observation here, when the die moves in a straight line which is parallel to the tube, so this called laminar. Okay, after a distance, the die no longer move in a straight line and show a wavy motion. So this called the transition flow. Okay, finally, the wavy die breaks up. So die particles get diffused in water and move in random motion. So this is called the turbulent. Okay, so this is the experiment from the Reynolds Osborne experiment. Okay, now this is also the laminar and turbulent flow, but this is using the candle smoke. Okay, the candle smoke here. So we get this is the turbulent flow and the laminar flow. Okay, smooth streamlines and highly ordered motion. So this is called laminar. Okay, turbulence, velocity, fluctuation, and highly disordered motion. So transition, the flow fluctuates between laminar and turbulent flow. Okay, so most flows encountered in practice are turbulent. So laminar and turbulent flow regime of candle smoke here. Okay, and the behavior of color fluid. Okay, based on the experiment, based on the Reynolds Osborne. Okay, so now we look at the laminar flow. Laminar flow is a path line. Each particles are parallel. Low velocity, viscosity plays a significant part in laminar. So the velocity profile of the laminar is parabolic curve. Okay, and the Reynolds number is less than 2000. So this is called laminar. Okay, for turbulent flow, so particles are in irregular path line. So high velocity, inertia plays a significant part in turbulence. Velocity profile shown as logarithm curve. So this is the turbulent here. Okay, so turbulent flow is Reynolds number is more than 4000. Okay, so using the Reynolds number here, so we use this formula. Okay, Reynolds number is equal to density times by the velocity times by the diameter divided by kinematic viscosity. Okay, and sorry, dynamic viscosity, and is equal to diameter times by the times by the velocity and divide by kinematic viscosity. So this is the formula for Reynolds number. Okay, so based on this formula, so we can classify it as the state of flow based on laminar, transitional, and turbulent. So the transitional is between 2000 to 4000. Okay, and less than 2000 is laminar, more than 4000 is turbulent. So this is the formula for Reynolds number, and we can know that the state of flow. Okay, look at example 4.1 here. Okay, so in a refinery oil with the SG 0.85 viscosity, sorry, kinematic viscosity, okay, the value here flows through a 100 mm diameter pipe at 0.50 liter per second. Is the flow laminar or turbulent? To get the flow laminar or turbulent, so the velocity, first you must find the velocity. So you get the velocity here 0.0637 meter per second, and then you get the Reynolds number. So just put all the value here and you get the Reynolds number. This is 354, so this is less than 2000. So the Reynolds number is less than 2000. The flow is laminar. Okay, look at the example 4.2 here. So with the SAE oil also in cast iron pipe. Okay, so to prove that the flow is laminar or turbulent, so you must find the velocity. Okay, you get the velocity 0.318, and then use the Reynolds number formula. So you find the 509.2. So this is less than 2000. So the flow is laminar. Okay, so for example 4.3 is also to find the flow would be transitional. Okay, so determine the range of average velocity to get the average velocity. Okay, for transitional flow 2000 to 4000, so we use the Reynolds number formula and get the velocity. Okay, so when Reynolds number is 2000, so we get the velocity is 4.424 meter per second. Okay, when the Reynolds number is 4000, so we get the value of velocity is 8.847 meter per second. So you get the value of range velocity. Okay, now for the flow to be in transitional state, so the average is based on 4.424 meter per second and 8.847 meter per second. So this is the calculation and solution for this question. Okay, so now we look at the friction in pipe. Okay, when fluid flows in pipe conduit, shear stress will be occurred. So when the pipe flow here, when the fluid flow in this pipe, conduit shear stress will be occurred, okay, along this pipe. Okay, so velocity in pipe will be decreased because of energy loss. So that can be measured by pressure difference. So this is called the HF, okay, the head loss. Okay, so using the Bernoulli equation, okay, so we use the Bernoulli equation that we have learned in topic 3 in chapter 3. Okay, so using the Bernoulli equation based on the section 2, section 1 to the section 2. Okay, and but for the topic 4 here, we must plus the head losses. Head losses can be minor or major head loss. So we call it as the head losses. So the head losses here based on this figure here. So H1, okay, H1, actually the H1 here, okay, at the Z1, okay, H is equal to H2 plus the HL here, okay, H2, okay, to get the HL here, H1 here, head losses in 1 here, is must equal to head losses in 2 plus the head losses H losses here H2, okay, H2 plus H losses. So actually H1 and head, okay, H1 and H2 is based on the here, okay, and the here. So we just call the HL here. So we use the Bernoulli equation. Okay, now the major head loss. So HLH losses can include minor losses or major losses. So major head loss HF, okay, this is called the friction head loss occur along the pipe. So this is the head loss. Sorry, head loss, major head loss. Okay, So minor head loss or HM is normal flow disruption, okay, based on the occur in entrance, submerge, discharge, contractions, expansion, pipe fitting bands, and elbow. So this is the concept for the friction pipe. Okay, so head loss or energy losses in pipe flow may be caused by friction, valve, fittings, expansion, contraction in pipes, diameter, and others. So frictional head loss is known as the major head loss. Okay, in pipe flow as the loss occur along the pipe, while other head loss such as due, valve, fitting, expansion, contraction are known as minor losses. So this is also can be estimated using the Darcy-Weisbach equation. Okay, so using the HF here. Okay, FL V squared over 2GD here. Okay, so this is the formula for HF. Okay, and when the laminar flow, okay, so we get the HF based on this formula. This is only apply for laminar flow. Okay, for laminar flow and turbulence and transitional, you can use this formula. HF is equal to FLV squared over 2GD. Okay, when you find that Reynolds number is laminar flow, so you can, to get the HF, you must use this formula. This formula is called Hagen-Poiseuille formula. Okay, equation. Okay, now this is Darcy-Weisbach formula. Darcy-Weisbach is the HF formula to get the turbulence, transitional, and also the laminar. Okay, but only for laminar flow, you can find the HF using this Hagen-Poiseuille formula. Okay, so this is the difference based on the Darcy-Weisbach formula and also Hagen-Poiseuille formula. Okay, for laminar flow, the friction factor can be calculated based on the Reynolds number. Okay, so the laminar flow based on the Reynolds number. Okay, so based on the HF for Darcy-Weisbach equation, so we use this equation. For Hagen-Poiseuille equation, we use this equation. So equating both equation, you get the F is equal to 64 times divided by RE. So we get the F based on the Darcy-Weisbach and Hagen-Poiseuille. So we use this formula for only laminar flow. Friction factor for laminar flow only. Okay, so now we look at example here. So diameter and length of pipe is given as 250 mm and 150 m meter respectively, which is used to flow, okay, 50 kg per second. Cross section at the point A is 35 meter higher than point B. By using Hagen-Poiseuille equation, determine the difference of pressure between two cross sections. So based on this cross section here, okay, so you get the value. Okay, the density given here and also the kinematic viscosity. Okay, so first you must find here. So this is the kinematic viscosity here, the value of kinematic viscosity. Okay, so first you must find the Q based on the mass divided by the density, so you get the Q. Okay, after that you find the velocity based on the Q divided by A, so you get the value of velocity. Okay, after you get the velocity, you must find the Reynolds number. Okay, put the velocity times by the diameter divided by the kinematic viscosity, so you get the value of RE is less than 2000. So this is laminar flow. Okay, so when the laminar flow, so using the Hagen-Poiseuille to get the HF. Okay, to get the HF or Hagen-Poiseuille, so you must use this formula here. Put all the value here until you get the value of this value, 18.47 meter. Okay, now using the Bernoulli equation or energy equation, using the based on the section 1 to the section 2 and plus the HF, so you can find the value of PA minus by PB. Okay, so ZA and ZB is 35. Okay, ZB minus by ZA is 35. Okay, so HF is 18.47 here. Okay, the VA and also the V is 0. Okay, because this is based on the concept of here. Okay, pressure of two cross section. Based on the cross section, so we get the value here, VA and the VB here. Okay, because at the velocity A and the velocity B with the same diameter, so they have the the same velocity A and the velocity B, okay, because we use the discharge, the same discharge, okay. So that's why the VA and the VB is VA minus by VB is 0. So that is called 0 here, okay. So then you get the pressure A minus by pressure B, so we get the value here, okay. So now look at the example 4.4 here, okay. Find the head loss due to friction, okay. So the head loss, find the head loss due to friction. So it's mentioned here as the HF, okay. So the to find F, the value of R must be obtained, okay. To get the head loss here, so you must find the Reynolds number, okay. So to get the HF, okay, so you must find the Reynolds number here, okay. So Reynolds number, put the value here and you get the Reynolds number is less than 2000, so the flow is laminar, okay. When the flow is laminar, you must use to get the F is based on this formula, okay, because this laminar, so you get the value of F is 0.04, okay. After you get the F here, you just put back again at the HF here, so you get the value of HF is 0.612 meter. Okay, so this is the calculation here. Okay, now look at the example 4.6 is also the same here. Okay, is the flow laminar or turbulent, find the head loss per meter. So to find the state of flow and find the head loss, first you must find the Reynolds number. Okay, find the Reynolds number to get the state of flow. So you get the flow is laminar. Okay, you get the flow is laminar. Then you find, first you must find the velocity first. Okay, because you want to use the velocity in Reynolds number formula. Okay, after you get here, you get the Reynolds number. Then you, because this is laminar flow, so you must find using this formula to get the F. Okay, after you get the F, so you use the formula of HF here. Okay, okay, because this formula can use for laminar flow, turbulent flow, and transitional flow. So you can find the HF here. Okay, but you must find the F first here. Okay, so you must find the F here. Okay, and put all the value here, and then you get the HF is 3.74 times by 10 power of -4 meter. So you get the value of head loss in pipe. Okay, now we look at the friction factor and Moody chart. So this is the friction factor and Moody chart. Okay, actually the friction factor is F. Okay, you want to find the F actually. Okay, using the Colebrook formula, using the last year's formula, okay, and also the Nicoresi and Prandtl formula to get the F. Okay, actually this is only for formula, the Reynolds number is between this here, okay, based on for smooth pipe flow. Okay, using the for fully rough pipe flow, using the Karman Prandtl, so we use this formula. Okay, and using the fully rough flow, Colebrook and Harlan, so we use this. Actually all this formula is given, okay, no need to worry, so because all this formula is given in your final. Okay, now this is the value of absolute roughness E for new commercial pipe. So you must look at this column, okay, to get the E, to get the roughness for the based on the type of pipe here. Okay, so now we look at the example here. Okay, water flows through a rough pipe. So when the rough pipe, so you use the E here. Okay, E is based on the rough pipe here. You can find the from the rough pipe type of flow. To find the type of flow, friction factor by using Karman, and pressure at A to get the A. Okay, first you must find the velocity. Okay, you get the velocity here, the value here. And using the rough pipe, so we get the E is 0.012. Okay, actually the rough pipe is not given. So this is not given the rough pipe here. Okay, so we actually the one pipe here based on 0.0 given here. Okay, actually the E is given. Okay, so the V velocity, you get the velocity here, and then first after you get the velocity, you get the Reynolds number. Okay, and then you get the Reynolds number is more than 4000. This is more turbulent. Okay, so after you get the Reynolds number, you use the Kalman equation, because in the question asks you to use the Kalman equation. Okay, so you use the common equation and you get the F here. Okay, after you get the F here, so you get the F. So find the HF, okay, to get the HF here, okay, based on the HF to put the F that you find from the common equation. So put the at HF. So Bernoulli equation between A and B. So we get here, okay, PA and PB here, okay. PB is open to the atmosphere, this is 0. Okay, and VA also 0. Okay, so VB, they have the VB here. Okay, so they just only have the PA. This is 0 plus the ZA is 30 meter. And the ZB is 55 meter. And the velocity B and also the HF here. So just put all the value here until you get the PE pressure at A is this value. Okay, so now we look at the Moody chart here. Okay, actually the Moody chart is based on the best information available and was plotted with the aid of equation here. Okay, so the chart often called the Moody diagram, or the quantities involved are dimensionless, so can be used for both BG and the SI unit system. Okay, so we get the based on the this is Moody chart here. Okay, the Moody chart here based on the this is the smooth pipe here. Okay, and also over E over D here. Okay, and based on the value here, E over D. And this is the Reynolds number and the friction factor here. Okay, so now we look at the example here to get the friction factor. Okay, so to get the friction factor based on the Moody chart. Okay, first you must find the Reynolds number. Okay, based on the velocity given. Okay, so find the Reynolds number here. So you get the Reynolds number is here. Okay, and this is more than 4,000. So the is turbulent flow. Okay, so stainless steel pipe is E is 0.002 because the stainless steel pipe. Okay, 0.002 because based on the Moody chart here, steel pipe here, stainless steel here. Okay, stainless steel. So we use the value here. Okay, 0.02. Okay, and then relative hardness E over D. So E over D 0.002 divided by the 25 mm. So we get the 0.0008. Okay, so from Moody diagram, so we get the F 0.0159. Okay, actually from the Moody diagram here, okay, 0.0008 here. Okay, so you get the 0.008. Okay, actually the 0.008. Okay, 40. Okay, actually for the 0.008 here, so you just draw the line here. Okay, actually draw the line. And Reynolds number is 2 here. Okay, 2.34. Okay, 2.3. This is 2 here. 2 is here. Okay, 2. 2.5 here. 2.3 is at this base. Okay, you get the number here. And then just take at this part here until you get the value of F 0.0159. Okay, so you get here F 0.0159. Okay, so now we look at example 4.9 here. Okay, so determine the head loss of friction when water flows through. Okay, to get the head loss of friction. Okay, so first you must find the velocity. So you get the velocity value, and then you find the Reynolds number based on the velocity. So you get the value here. This is turbulent. Okay, so now you look at the value here. So Reynolds number here, and the value E over D. So E over D, you get the E over D is based on this roughness here, 0.001. Okay, so just look at the Moody chart. So based on the Reynolds number here, okay, just put the Reynolds number here, and we know that the blue line here is 0.001. Okay, relative roughness here, and just take here. So you get the F is 0.021. So you get the value of F here based on Moody chart. Okay, so then after you get the F, so you must use this formula to get the HF. Okay, so you get the value of 17.14 meter. Okay, so this is the concept to get the F from Moody chart and also the FHF. Okay, so to get the F in Moody chart. Okay, that's all. So we continue in part B. Assalamualaikum warahmatullahi wabarakatuh and thank you.